We will now speak about Maxmin strategies. These make particular sense in the context of zero-sum games, but actually are applicable quite to all games. What is a Maxmin strategy? It's simply put a player's strategy that maximizes their payoff, assuming the other player is out to get them. We will concentrate primarily on the two-player case here, again, because when we get to zero-sum games, those really make only sense in the case of two players. But keep in mind that one could define this kind of more generally when we speak about Maxmin strategy. So the Maxmin strategy is a strategy that maximizes my worst case outcome, and my Maxmin value or safety level is that payoff that's guaranteed by the Maxmin strategy. And here it is defined formally. The Maxmin strategy for player I is the strategy S1 that maximizes the minimum that the other player, remember that minus I is the player other than I, would hold player 1 down to. And the Maxmin value is defined similarly to be the value of that Maxmin strategy. Now, why would we want to think about the Maxmin strategy? One can think of it either as a simply a sort of a certain cautionary. Maybe the other people will make some mistakes and not act in their own best interest. Maybe I'm not sure exactly what their payoffs are. There are a lot of interpretations, or you can simply be paranoid about them and think that they're out to get you. And you know the saying, even the paranoid have enemies. That's the Maxmin strategy. And just to confuse things, we'll also speak about the min-max strategy. The min-max strategy is strategy against, if you wish, the other player in the two-player game, is a strategy that minimizes their payoff on the assumption that they're trying to maximize it. And so here is the formal definition. The min-max strategy for player I, who's playing against the other guy, which we denote by minus I, is the strategy that minimizes the maximum payoff as attempted by the other guy of the payoff to the other guy. And the min-max value is simply the value of that min-max strategy, the value to player 1. Now, why would player 1 want to harm the other guy? Well, you could just be out to get him. That's a possibility. Or they could be playing a zero-sum game, and in a zero-sum game, hurting the other guy is tantamount to improving your own payoff. And so, in the setting of zero-sum games, max-min and min-max strategies make a lot of sense. And in fact, in a very famous theorem due to John von Neumann, it proved that in a zero-sum game, by definition, we consider only two-player such games, any Nash equilibrium, the player receives a payoff that is equal to both his max-min value and his min-max value. And that means that, so we'll call it the value of the game. The value for player 1 is called the value of the game. And that means that the set of Maxmin strategies are really the same as set of the min-max strategies. That is, trying to improve your worst case situation is the same as trying to minimize the other guy's best case situation. And any Maxmin strategy profile or min-max strategy profile, because they're the same, constitute a Nash equilibrium. And furthermore, those are all the Nash equilibria that exist. And so the payoffs in all Nash equilibria is the same, namely the value of the game. One way to get a concrete feel for it is graphically, and here's the game of matching pennies. This is a game where each of us chooses heads and tails with some probability, and if it comes up either if the result of our randomization I end up choosing head and you end up playing tail, you win, and vice versa. Also, if I chose tail and you head, but if we both chose head or both chose tail, I win. And so here are the payoffs. You see here the strategy spaces. This is player 2 is kind of increasing their probability of playing heads, and this is player 1. And on this dimension, you have the value of the game, the payoff to player 1. And the only natural equilibrium is for both to randomize 50-50. It's this right here. It's conveniently looked by slicing the three-dimensional structure in this way, and you sort of see that it's got to be an equilibrium in the sense that player 1 could be moving along this curve, but as he does it, his payoffs would only drop, and so he's trying to maximize the value. He wouldn't do it, and conversely, player 2 can only traverse along this, but if he does that, the payoffs would only increase, and he's trying to minimize the value. So you get a stable point, which for obvious reasons is called a saddle point. In general, we can use the min-max theorem to compute the equilibria of zero-sum games, and we do it by simply laying out a linear program that captures the game, and here it is. So U1 star is going to be the value of the game, that is the payoff to player 1 in equilibrium. And so we're going to specify from player's 2 point of view. We could have done it the other way around also. So what player 2 is saying is simply says, for each of the actions of player 1, each action that player 1 might consider, I want to find a mixed strategy S2. So here's my mixed strategy S2. It will look at all my pure strategies K and make sure that the probability, that's the probability distribution over those. They sum to 1 and they're non-negative. So what I'd like to do is that the best response to my strategy by player 1 for any of these actions will never exceed this value of the game, because I'm trying to minimize it. So I'm going to find the lowest U that has a property that player 1 doesn't have a profitable deviation by any of his pure strategies. So when I look at the payoff for player 2, when I play A2K and he plays A1J, that J that I'm considering right now, and I multiply the probability of, in my mixed strategy, playing A2K, I don't want that player 1, that other player 1, to have a profitable deviation. So it's got to be that his expected payoff will be no greater than the value U1 star. So clearly this is a correct formulation of the game, and it is a linear program. As we know, linear programs are efficiently solvable, in theory by a interior method that is provably polynomial, in practice by procedures that are worst case exponential, but in practice work well.